All right, so we were talking about when n equals 2, if we have two monomorphisms that are linearly dependent, then they must actually just be equal on the nose. Okay, you can't have one being a multiple of the other. So let's prove that. So proof when n equals 2. Okay, and just to keep with the book's notation, I'm gonna get rid of m. So let's suppose mu and lambda from k to l are monomorphisms. And in fact, not only do we have a way of multiplying, if these are extensions of, say, some common field m, not only do we have a way of multiplying by m, but we also have a way of multiplying by L. So we claim that mu is a lambda for any a and L implies mu equals lambda. So a has to be 1. Now remember, these are functions. The functions output in L. So I can scale by L after applying the function. And that's what this is doing. It's scaling by L after applying the function. Okay. So just to be really precise, a lambda of some little k, what does that function do? It first applies lambda. Now I'm in L, and then it multiplies by a. All right, so let's prove this. How does this work? Well, suppose such an a exists. Then what does it mean that two functions are equal? It means that whenever we plug in any element of our field, the input, our domain, that this is a terrible mu, sorry, that the outputs have to be the same. So two functions are equal if and only if they agree on every input. Okay. So what we're going to do is we're going to use this, but we're going to replace our x with yx. Okay. And when we do that, we're going to get mu, because right, yx is an input. If y is in k and x is in k, yx is also in k, so that's an acceptable input because we have a field. So they have to agree on every input, so this must be true. But now we're going to use the field structure. Right? So what do we get from this? We get that mu of y times mu of x should be a lambda of y, lambda of x. Okay, so here's one equation. I'll call that 1. Or I'll call this one up here 1, and this one 2. Let's also multiply 1 by mu of y. Mu of y is just some number, some element of L, depending on what y is. And we're going to take this guy up here, and we're going to multiply by mu of y. When we do that, we get mu of y, mu of x is, sorry, I want to multiply not by mu of y, I want to multiply by lambda of y, sorry. Lambda of y, there we go. Lambda of y, mu of x is a lambda of y, lambda of x. All right, so let's look at these two guys that I have here. That is the same as that. So these guys must be the same. Lambda of y, lambda mu of x. And this is for all x, y, and k. Let's just set x equal to 1. Then mu of 1 is certainly 1. So these guys become a 1. Oops, meant to use that becomes a 1. That becomes a 1. We get mu of y is lambda of y, and this is for all y and k. So mu and lambda agree on all inputs. So mu is equal to lambda. Now notice, So that's what we wanted to show, right? If they were multiples of each other, they must be equal. Multiples of each other when n equals 2 is the same as linearly dependent. So what we wanted to show. And notice we had to use the field structure. We used the field structure right here. It showed up right there. So this is not, so in this example we had this guy, this 2i would not have worked because it does not break up under multiplication, irrelevant of what the domain and codomain are. It doesn't break up under multiplication. So the field structure is crucial, and it shows up right here in order to separate this and then multiply the other one by lambda. It recreates the right hand side, and then you can finally compare. We also use the field structure right here, oops, when we sort of cancel the mu of x on both sides, right? So I'm just emphasizing it's very important that we are dealing with fields, and we are dealing with very specific functions, monomorphisms. It's not true in general for vector spaces without the field structure and the extra conditions on the function.